Share my screen. Here it is. Okay, so we're going to continue our discussion of electrochemistry. Oh, let me erase this from. All right, so as I said before, we'll be continuing our discussion of electrochemistry. And of course, you recall that when we were here the last time, we were talking about balancing redox equations. And as you're going to see, this is very important in this chapter because pretty much, well, not pretty much, all the reactions we'll be looking at and the concepts involving these reactions in electrochemistry are redox reactions, right? So in all of these reactions, you're going to see where you have electron transfer from one substance to the other. All right, so let me start off today's class with this diagram right here, which is representing what is called what is an example of what is called a galvanic cell. Now, before I get into this, let me just say that if you recall at the intro of this chapter, I said that there are two types of reactions we'll be looking at. They're all redox reactions, but there are two types of reactions we'll be looking at. One where the reaction is spontaneous and it produces electrical energy, which is what we'll be discussing now. And then the other type of reactions we'll be looking at are those reactions where electrical energy is used to drive a non-spontaneous reaction. All right, so let's look at what is called a galvanic cell, which basically is a device which produces an electric current, all right, using redox reactions. So let me just describe what we have here. And this is a simple example. There are some other more complex examples, but this is a simple example to illustrate how this works. So we have two beakers, one containing zinc sulfate and the other one containing copper 2 sulfate. Both are soluble in water, and therefore you're just going to have zinc and sulfate ions floating around here. And in this case, copper 2 plus and sulfate ions floating around, all right? So these ions will be free to move around, mobile, very important for us to recognize that. Into this particular solution, we have here that is dipped in it a piece of zinc metal, right? And it's connected to this copper metal, which is dipped into the copper 2 sulfate solution, right? It's connected by electrical wire, and you'll notice that there's an instrument here, which is called a voltmeter. And the voltmeter measures, where's my pen? Oh gosh. The voltmeters measure the potential, what is called the cell, it measures what is called the cell potential. And basically the cell potential is basically, well, one simple way of looking at it is the tendency of the electrons or the electric current to flow through the external circuit, all right? So that's a part of the circuit here. So basically, when everything is turned on, the electrons will flow, and therefore the voltmeter will pick up on that, all right? Now let's look at this in more detail. Where the electrons come from in this particular case? Well, the electrons here, emerging from the zinc anode, comes from the oxidation of zinc, according to this equation right here, all right? So as you can see here, the zinc will undergo oxidation by the loss of 2 electrons to form the zinc ions, right? So basically, the zinc ions will enter the solution, while the electrons being produced will enter the external circuit, right? And basically, you're going to have a flow of electrons through the external circuit, which means that electrons would be actually entering this copper here and will enter the solution. And what will happen at this end is that the copper 2+ ions will undergo reduction because it will gain the 2 electrons from the copper electrode here. So this is the equation for the reduction of the copper, right? Or I should say, the reduction of the copper 2+ ion, right? So the copper 2+ ion here will gain 2 electrons to form the copper solid, right? So basically what we are having here is a redox reaction, right? Where oxidation will take place at the anode. This is called the anode, by the way. In fact, here, right, at the anode, which is the zinc metal here. In fact, I would say the entire combination of the zinc dissolved, or not dissolved, but dipped in the solution, that's called the anode, right? And at the anode is oxidation taking place, as I said before. And then at the other end here, we call this the cathode, where reduction takes place. As we said before, the copper 2+ will gain 2 electrons to form the copper solid, right? So this is something that spontaneously happens. If you remember, we said from the previous chapter, when we talk about a spontaneous process, that means that the process will occur without any intervention on anybody's part. And this is basically what will happen. When you set this up, the current will just start flowing from the anode to the cathode, all right? So this would be the net equation, right? Of course, you know how we get the net equation. We simply add these two together and we cancel out the common items on both sides, which in this case would be the electrons. And that's how we get the overall equation for this reaction, all right? So this is basically what happens in what is called a galvanic cell, right? And this is how an electric current is produced in such a cell. And oh, one thing I forgot to mention. You'll notice as a part of the setup, you have what is called a salt bridge, right? The salt bridge is necessary for the current to continue, because without the salt bridge, what will happen is that the concentration of zinc will increase to such an extent that basically this becomes more positive, and that will prevent more electrons flowing from here to the other side. And then in the case of here, the copper 2+ concentration would be reduced, which means that overall the solution will become more negative, right? So that's what would happen without the salt bridge. Now, with the salt bridge, by the way, the salt bridge is basically consists of agar gel soaked in potassium chloride. You could use also sodium chloride as well. And basically what happens is that in the case of, as I said before, at the cathode, the zinc ions will build up. So therefore what will happen in the presence of the salt bridge is that the zinc ions will move into the salt bridge and the chloride ions will move from the salt bridge into the solution in order to maintain electrical neutrality, and therefore the current will not prematurely stop. In the case of the anode, because copper 2+ is being reduced to form copper ions, there'll be an excess of sulfate ions. The sulfate ions will make the solution more negative, and therefore in order to regain neutrality, the sulfate ions will move into the salt bridge, and simultaneously the potassium ion will move into the solution, and therefore neutrality will be maintained, and therefore the current will basically continue, all right? So that's basically the role of the salt bridge in this setup. Okay, so some things we want to say here about galvanic cells. As I said before, as a part of the setup, you have what is called a voltmeter, and the voltmeter measure what is called the potential difference, but there's some other terminology that is used to express what we're measuring in that instance. You can call it the cell voltage, the electromotive force, and the cell potential, right? These are all different terms that is used to describe what is measured using the voltmeter when it's a part of that setup, right? The electromotive force is a bit of a misnomer. It's a holdover from a term that used to be used back in the day because it was believed that there's an actual force that is forcing the electrons through the wires of the external circuit. But we now know that not to be true, but this term is still being used in some textbooks, all right? We can represent a galvanic cell, such as the one that we just looked at, using what is called a cell diagram, right? So this is the overall equation of the reaction that we just looked at. in the galvanic cell that we just looked at. So the cell diagram that we'd use for this will be, well, in this particular case, the concentration of the copper 2 plus and the zinc 2 plus ions in that solution is 1M. And that's important in order for us to determine or write down what the cell diagram is. So this is what the cell diagram for this particular cell looks like, right? Now, typically what we do is that we have the anode on the left and the cathode represented on the right. So at the anode, as we said before, you have oxidation. In this case, it's a zinc undergoing oxidation to form zinc 2 plus. So we write it like this, zinc, and then we have a line like this, and zinc 2 plus. And the states are very important. It's not included here, so let me just include it here. We have solid here, and the zinc, of course, will be aqueous, right? And we have to put the molarity as well, which is 1M. And then we have a double line here, which basically represents a separation between the two electrodes. And then we have copper 2 plus aqueous, 1M, and then copper solid. And we put the copper 2 plus aqueous first because it's a copper 2 plus, which is undergoing reduction to form copper, all right? Over here, the zinc is placed first, and then the zinc aqueous, because we have zinc as the reactant here, and zinc 2 plus will be the product as a result of the oxidation, all right? So that's just a shorthand way of representing a galvanic cell based on its composition and concentration and so on. All right? Okay, so now one thing before I go to the next slide. One thing I should say here concerning the measurement of the cell potential. The cell potential, by definition, is a difference in the values of the potential of one electrode compared to the other, right? The problem is, even though we have that definition, it is impossible for us to measure absolutely the potential of one cell and the potential of the other and then find a difference, right? Because in order for us to measure the potential of anything, we have to have both half cells hooked up to each other to get one cell, all right? So what was decided by the powers that be is that we defined what is called the standard electrode, which is basically assigned a potential of 0, and therefore we get the other values of other electrodes compared to that particular electrode. And the electrode that is used to establish that 0 point is called the standard hydrogen electrode. And this diagram here basically shows what it looks like. It's basically a solution of 1 molar acid, typically hydrochloric acid. You have an electrode, a metal, platinum, which is inert, so therefore it will not react with the acid. Basically, the platinum serves as a conduit in terms of electrons leaving or exiting this electrode. And then we have hydrogen gas here being forced into this tube where the platinum electrode is located. That gas has a pressure of 1 atmosphere, right? So those are the standard conditions. 1 atmosphere, 1 molar for the hydrochloric acid solution. And I should add that the standard temperature, let me include that here, and temperature standard is equal to 25 degrees Celsius, all right? So those are the standard conditions, the same standard conditions that we learned about with respect to thermodynamic state functions like enthalpy, entropy, and so on. So this is the standard hydrogen electrode, sometimes called She. And as I said before, this is the equation for the reaction that takes place in this electrode, the reduction equation. It's 2H plus 2 electrons to form H2. That's the equation, all right? And this is assigned the standard electrode value of 0 volts, right? And of course, we have a small o here as a superscript that represents standard. Just like we saw in the case of standard free energy, standard enthalpy, standard entropy, and so on, all right? So that is basically the electrode that is used to establish the 0 value for the standard electrode potential. And then any other electrode hooked up to that will basically, its value will be determined based on that standard, all right? And let me just say here, I think I skipped over it, the standard reduction potential is a voltage associated with a reduction reaction. And this is very important, as you're going to see shortly, right? I might abbreviate it and just call it standard electrode potential. But it's actually a reduction or value representing what is observed in terms of the voltage for a reduction half reaction. So as you can see here in the case of the hydrogen electrode, this is the reduction half reaction, and that is set at 0. Okay, so how do we determine the reduction potentials of other electrodes based on this? Well, what we do, as I said before, is that we hook up the particular electrode to the hydrogen electrode, the standard hydrogen electrode, right? So in this case here, we're hooking up the zinc sulfate or the zinc electrode to this, right? And what we observe is that there'll be a flow of electrons from the zinc electrode to the standard hydrogen electrode, right? So what does that tell us? Well, before we do that, this is the cell diagram for this particular cell, right? So the zinc is undergoing oxidation to form zinc 2+, right? And this has a 1 molar solution. And again, this should be aqueous. Put that here. This should be aqueous here, right? And then we have the 2 lines, and then we have the different items for the hydrogen electrode. This should be aqueous here, and this should be a gas here, all right? And so therefore, this is the cell that results when you hook up the zinc electrode to the hydrogen electrode. Also, as a part of the diagram, you have the PTE platinum electrode here. That is also included. You need to include that because even though it's not actively involved in the reaction, but it serves its purpose as a conduit for the electrons going either into the electrode or out of. Okay, so basically, as we said before, what was observed is that the electrons will move from the zinc electrode to the standard hydrogen electrode. So therefore, obviously that means that the zinc is undergoing oxidation. So that would be the oxidation equation for the zinc. And then for the hydrogen electrode, that is where reduction takes place. And this would be the equation, right? The hydrogen ions will pick up electrons to form H2. So when you add these two, the electrons will cancel out, and you're going to end up with this as your equation, all right? Your overall equation for what's happening in this particular cell. Now, how do we determine the actual electrode potential of the zinc relative to the hydrogen electrode? Well, firstly, you have to measure the difference based on the instrument here, and that is 0.76, right, volts. So when you set it up and you include your voltmeter, that's what you're going to get as your reading. Now, the standard EMF of the cell would be equal to the standard EMF of the cathode minus the standard EMF of the anode. That's the definition of the standard EMF of the cell, right? Now, we know that because zinc is undergoing oxidation here, that means that this is the anode. And that means obviously that this would be the cathode because reduction takes place here, all right? So we know that the EMF of the cell, as I said before, is equal to 0.76, right? And we also know that by definition, because we're dealing with the hydrogen electrode, this EMF here for the cathode would be 0, right? So this would be 0 volts, and this would be 0.76 volts, right? So we can find out now what the EMF standard of the anode is, right? So this is the equation here. We know that the EMF of the cell is 0.76, and we know that the EMF of the hydrogen electrode by definition is 0. So therefore, we can calculate the standard EMF of the zinc electrode, and that would be equal to minus 0.76 volts, all right? So that's how we will get the standard electrode potential of the zinc electrode when it's hooked up to the standard hydrogen electrode, all right? Okay, any questions about this? Any questions? Any questions? Okay. Another way, oh, and by the way, you can also represent it this way. Zinc 2 plus 2 electrons give you zinc, and the standard EMF value for that would be minus 0.76. Okay, so let's look at another instance. Now in this case, we're hooking up the same standard hydrogen electrode to the copper electrode, as shown here, right? In this case, what was discovered was that the electrons will be flowing from the hydrogen electrode to the copper electrode, right? So therefore, what that means is that as far as the hydrogen electrode is concerned, it's undergoing oxidation. And as far as the copper electrode is concerned, it's undergoing reduction. All right? So with that in mind, and also let me point out that when this is set up, it was determined that the standard EMF of the cell itself is 0.34 volts. All right? Okay, so since we have identified the cathode and the anode based on the flow of electrons, so let me just put here anode, and this is the cathode. All right, just to make sure that we know what is what. All right, so to find the EMF, so this is the anode reaction, and that's the cathode reaction. All right, now to find the EMF, that's the net equation, right? Again, it's always a standard EMF value for the cathode minus that for the anode, right? Now, we know that because the anode is the standard hydrogen electrode, its value is going to be 0, and we know that the EMF of the cell is 0.34 volts, right? So all we have to do is put the numbers in, right? 0.34 volts will be equal to the standard EMF of the copper electrode minus 0, which means that the standard EMF of the copper electrode, would be equal to 0.34 volts, all right? So that's how you get the standard EMF value for the copper 2+ electrode when it's connected to the standard hydrogen electrode, all right? Okay, any questions about this one? Any questions? Any questions? So, based on those kinds of measurements, tables have been developed, and that is what I'm going to show you on the slide, right? Which gives you different standard EMF values for reduction half reactions, right? So if you can imagine what we just described being done on a large scale to using different half cells, hooked up to the standard hydrogen electrodes, these are the values you're going to get. And I have a more comprehensive list in Canvas. Let me just show you where that is, because that is what you'll have access to during your tests. Okay, let me see here. Okay. All right, so files, and then tables. Where are your tables? Tables. Okay, and where it says, oh shoot, I thought I had it here. Oh, here it is, standard reduction potential, right? So let me just download that so you see what it looks like. All right, so this is a table you'll have access to. So you may want to have a look at it to get familiar with it. These are all half reactions, reduction half reactions, and this corresponding standard electron potentials, right? Now, if I remember correctly, this table organizes the half reactions according to the magnitude, highest to lowest, of the EMF values. That's part of it. The other part, I think they have it in alphabetical order of the substances formulas on the left side of the half equation, right? So those are two ways they're arranged. So this is the table that you'll have access to when it comes to solving problems, such as the ones that we're going to see shortly. So let me go back to okay. So couple of things I want to say here about these values before we look at some examples. Firstly, the standard EMF value is for the reaction as written, all right? So basically all of these here are reduction half reactions, and these E values are associated with the way these equations are written, all right? The second thing I want to make note of is that the more positive the standard EMF value, the greater the tendency for the substance on the left side of the equation to be reduced, all right? So for example, of all of these here in this particular table, fluorine has the greatest tendency of being reduced because its EMF value for its reduction is the highest at plus 2.87. Another thing I want to say here is that half cell reactions are reversible. And when that happens, when you reverse the reaction, the sign of the EMF value changes. So again, going back to the fluorine example, the fluorine being reduced by 2 electrons to give 2F minus, its value is 2.87. So the reverse, which would be 2F minus to give F2 plus 2 electrons, the EMF of that value would be minus 2.87 volts, all right? So this is kind of similar to what we learned with respect to delta G and delta S and delta H, right? When the equation is reversed, the sign is changes, all right? The next thing I want to say here about standard EMF values, which is very different from what we learned with respect to enthalpy and entropy and all that, and that is that when you multiply the equation by a certain number where all the coefficients are changed, the EMF value standard does not change, right? The standard EMF value does not change if you multiply the equation by any number, all right? So as stated here, changing the coefficients does not change the value of E0, but the equation still must be balanced. That's the important thing, right? The equation must be balanced, but even if you multiply by 2, 3, 4, whatever, the value does not change as far as the standard EMF value is concerned. And that's also very important when it comes to solving some of the problems that we'll be looking at shortly. All right. In fact, I think the next slide is an example. Yes. Okay. So this question says, what is the standard EMF of an electrochemical cell made up of cadmium electrode in a 1.0 M cadmium nitrate solution and a chromium electrode in a 1.0 M chromium nitrate solution, right? So how do we solve this? Well, the first thing I would do is I would write down the equations for the reductions of those ions, and I would look up the standard EMF values for those particular half equations, right? And this is what you're going to end up with, right? So in the case of the first one, the cadmium 2 plus 2 electrons to give you cadmium, the standard EMF value, if you look it up, is going to be minus 0.40 volts. And in the case of the chromium 3 plus undergoing reduction to form chromium, the standard EMF value, if you look it up, is minus 0.74 volts. Yes, ma'am. In the table that I just showed you, right? So yeah, so you're going to need those values in order to solve this problem, all right? Now, based on what we learned earlier, remember we said that the higher in value the standard EMF value, the more likely that reaction or that half reaction will occur as written. So when you compare these two, the one that is higher in value would be this one right here, minus 0.40 volts. So therefore, we know that this reaction will occur as written, and this reaction will occur in the reverse. So basically, as far as the oxidation is concerned, it's going to be the chromium undergoing the oxidation to form chromium 3 plus, losing 3 electrons, and the reduction reaction at the cathode would be this equation, which will remain unchanged. So you're just going to rewrite that there, all right? And of course, because this one is reversed, right? The standard EMF value for that particular half cell would be plus 0.74 because previously was minus 0.74. This does not change, so therefore this does not change, right? So when we add these two together, well, before we add them, of course, like in the case of all redox reactions, we have to make sure that the number of electrons lost and gained are the same. And you remember how to do that, right? In this particular case, what do? How do we get the number of electrons lost and gained being the same? Multiply this one by 2 and this one by 3. Exactly. Multiply that by 2, multiply that by 3, and then we add them together and we get the net equation, right? But we do not multiply these numbers here, right? Remember what we said. The EMF values does not change when you multiply the equations by any number. So basically these remain the same. So to get the EMF of the net equation right here, we simply add the 0.74 to the minus 0.40, and that gives you the answer, which is what the question is asking for. All right? Another way of doing this is simply using this equation that we saw before. The standard EMF of the cell would be equal to the standard EMF of the cathode minus the standard EMF of the anode. So in order for you to use this equation, you have to identify which is which. Which half cell is the cathode, which half cell is the anode. The cathode is where reduction takes place, so that means that the EMF of the cathode in this case would be the minus 0.40 volts minus the EMF of the other electrode, which is the anode. So that's the setup, minus 0.40 minus 0.74, and that will give you the same result, right? So I'm just showing you two different ways of solving this problem. Admittedly, this might be easier, but you have to be careful because in this particular case, if you're using this method, you have to make sure you identify correctly which of the two electrodes will be the cathode and which is the anode, right? The cathode is where reduction takes place, and the anode is where oxidation takes place. Once you identify those two, then you can plug those numbers into that equation, and that will give you the standard EMF of that particular cell. Okay, any questions about this particular example? Any questions? Okay. Any questions out there in Zoom? Any questions out there in Zoom? Okay, I'll take your silence to mean that you understand this completely. All right. So I think, hold on. Okay, let's talk about spontaneity. So some things that we learned in the previous chapter with respect to thermodynamics will apply or will apply here, right? So we know what we mean by the term spontaneous, right? The reaction or the process will take place without any intervention. And it turns out that the free energy, which is used to tell whether or not a reaction is spontaneous, is related to the EMF of the cell by this equation right here. Delta G is equal to minus N times F times the EMF of the cell, right? Now, N is the number of moles of electrons that is transferred from the substance which is reducing to the substance which is transferred from the substance which is undergoing oxidation to the substance which is reducing or being reduced, all right? So that's what N is. F is a constant known as a Faraday constant, and it has a value of 96,500 joules per volt per mole or 96,500 coulombs per mole. Now, I don't know if you have met this term coulomb before. Coulomb is basically a unit of charge. Unit of charge. And basically Faraday's constant represents the number or the amount of charge that is carried by 1 mole of electrons, right? So 1 mole of electrons would carry a total charge of 96,500 coulombs, all right? So this is the equation which relates the free energy to the EMF of the cell, and this is the equation which relates the standard free energy to the EMF of the cell, right? So the only difference between them is that this gives you the free energy under standard conditions, and this is delta G for any conditions, including standard, all right? Now, it turns out that delta G, or not turns out, we know this already, that delta G standard is equal to minus RT ln K. So since delta G standard is equal to minus RT ln K, and delta G standard is also equal to this right here, we can equate these two, right? So therefore, delta G is equal to minus RT ln K, which is equal to minus NF EMF of the cell, all right? So we can rearrange this to get the standard EMF of the cell will be equal to RT over NF times ln K, all right? So if we put all these numbers in, and these are all constants, the R is a constant, 8.31, T is 25 degrees Celsius because we're talking about standard conditions here. And as I said before, Faraday's constant is F, right? So we put all these numbers here and we're going to end up with this equation right here. This is just showing you the units canceling out. And you're going to end up with this equation right here. The standard EMF of a cell is equal to 0.0257 volts over N. Remember again, N is the moles of electrons undergoing the transfer from the anode to the cathode. And we can also express the EMF of the cell if you're going to use log to the base 10 instead of log to the base E, then it turns out that the EMF of the cell is equal to this as well. So these two are basically two different ways of saying the same thing, all right? And of course, these two are saying the same thing as this equation right here, all right? So 3 different ways of saying, expressing the relationship between the standard EMF of the cell and the equilibrium constant, So based on what we have just learned here, these are the relationships that we have just learned between delta G, which is the standard free energy, K, which is the equilibrium constant, and the standard EMF of the cell, right? And this is a triangle that's basically showing you the different relationships. So if you want to find delta G based on K or vice versa, this would be the equation you would use. If you want to find delta G standard versus the standard EMF of the cell, this is the equation you would use. And if you want to find a relationship between the EMF of the cell and K, this is the equation you would use, all right? So, and I think, if I'm not mistaken, all these equations, or maybe one or two of them, should be in the tables that I've posted in Canvas, all right? Okay, so let's apply, before we get to the actual example. So this is again just showing you the relationship between delta G standard, K, and the standard EMF of the cell. If delta G is negative, which means that the reaction is spontaneous, that means that K must be greater than 1, because here, K would have to be greater than 1 in order for minus RT ln K to be negative, and the standard EMF of the cell must be positive, right? Now, if delta G is 0, that means that K is equal to 1, and that means that the standard EMF of the cell must be equal to 0 as well. And then if K, or I should say if delta G is positive, which means that the reaction is non-spontaneous, that means that K must be less than 1, which would mean that this is negative. Negative times negative gives delta G being positive, and that means that the standard EMF of the cell must be negative, all right? And basically, over here on the right side of this table, it tells you exactly what the situation is in terms of the product outcome or the reaction outcome. So if delta G is negative, that means that the reaction favors the product. If delta G is equal to 0, that means that both reactants and products are equally favored. And if delta G standard is positive, that means that the reaction favors the formation of the reactants. Okay, so let's look at this example here based on what we have just covered. Oh, sorry, yes, ma'am.
There's a question about like the two previous there. How do you get log instead of ln later on? How do you get log instead of ln?
Well, what I was saying was that if you prefer to use log to the base 10 instead of ln, then that transfer, that basically converts this number into a different number. I don't remember the exact relation. You know what? I think I can figure it out. Hold on. It's been a while since I've done this. Okay, so the relationship between L and K, and log K is ln K is equal to 2.303 log to the base 10 of K, right? So basically what you do is put this where this is, where the ln K is, and the result would be the last equation, all right? Okay, all right, so let's look at this example. This question gives you the equation here, and it's asking for the equilibrium constant for that equation, right? So this is the equation that would apply. You need to find the standard EMF of the cell first before you can find K, all right? So how do we find the standard EMF of the cell? Well, we have to split up the equation into the redox or the oxidation and reduction part. So as far as oxidation is concerned, this is the equation, and you'll have to look up the EMF value for that. For the reduction, that would be the equation, right? Fe2 plus 2 electrons to give Fe. And of course, you'll notice that there are 2 electrons being transferred. So that's important because that gives you the N value. So N is equal to 2, all right? So now what we have to do is calculate the standard EMF of the cell. And that would be equal to the EMF of the cathode minus the EMF of the anode. So we already identified the cathode as being the iron half reaction or half cell, and that of the cathode would be the silver, So we look up those values, right? And we plug them into this equation, and you're going to get the standard EMF of that cell be equal to minus 1.24. So this value here, the minus 1.24, is what's going to go here, right? So we have that value already. We have the end value. So all we have to do now is rearrange this equation to solve for K. When you do that, this is what you're going to end up with. K will be equal to E to the raised to the EMF of the cell times N divided by 0.0257 volts. And then we simply put the numbers in, right? So for the EMF of the cell, that will be minus 1.24 volts, multiplied by 2, divided by the 0.0257 volts, and then you find E to that value, and that will give you the K value. And it turns out that the K value will be equal to 1.23 times 10 to the minus 42. And let me just say that in order to make sure everything is straight as far as sig figs is concerned, this should actually be rounded off to 2 sig figs. So let me just cross over this 3 here. So the actual answer should be 1.2 times 10 to the minus 42. All right? Okay, any questions about this example? Any questions? No questions? Okay, let's see here. What about the effect of concentration on the EMF of the cell? Because so far, what we have been discussing is situations where the molarities of the solutions involved is 1 molar. So this brings us to this equation right here. The free energy of a reaction is equal to delta G standard plus RT ln cube. This is an equation that we met before. And delta G standard, of course, we know is equal to minus NFE. And delta, well, I'm sorry, I take that back. Delta G is equal to minus NFE, and delta G standard is equal to minus NFE standard, right? So when we plug delta G NFE here and NFE standard here, this is the equation we end up with, and we can rearrange this to get this equation right here, and this is called the Nernst equation, right? This equation relates the EMF of the cell to the reaction quotient, all right? Which of course is dependent on the concentrations of the species involved in the reaction, all right? R, of course, is the molar gas constant, T is the temperature, F is Faraday's constant that we met before, and N is the number of electrons transferred. And again, if you put the values of R, T being 298 Kelvin, and the value for the Faraday constant, you're going to get this equation converted to this equation right here. All right. And again, if you want to express your value in terms of log to the base 10, this is another way of expressing it. So again, these two are different ways of saying the same thing. All right. Okay. So that's basically showing you the relationship between the EMF of the cell and the concentration as reflected in the reaction quotient. So let's apply this to this example right here. It says, will the following reaction occur spontaneously at 25 degrees? And it gives you the concentrations of the iron 2 plus and the cadmium 2 plus. This is the equation. So basically what you need to do is find the standard EMF, right? Or the EMF of this reaction, not necessarily the standard EMF, but the EMF of this reaction. If the EMF of the reaction is positive, that means that the reaction is spontaneous. If it is negative, that means the reaction is not spontaneous, right? So how do we do that? Again, we separate the two equations into the oxidation and reduction equations. The reduction reaction is taking place in the cathode. The oxidation reaction is taking place in the anode. Again, we identify the number of electrons transferred, which again, in this case, is 2, which means that N is equal to 2. And then we find out what the standard EMF is. So we have to go to the tables and we have to look up the standard EMF of the iron and the cadmium half-cell reactions. And because we know what is the reduction and what is the oxidation reaction, we know therefore that this here would be the cathode reaction. So therefore it's cathode minus oxidation EMF values. So when you consult the tables, this is what you get. For the iron, you're going to get minus 0.44. For the cadmium, you're going to get minus 0.40. So the standard EMF of this reaction will be minus 0.04 volts. Now that's the standard reduction potential, not the actual reduction potential. In order for us to calculate that, we need to determine what Q is first, right? Because this is the equation that we're gonna use, right? So far, we have N, which is 2, and we have the standard EMF, which is minus 0.04 volts. So we need to find Q. So based on this equation here, Q would be equal to the concentration of the cadmium divided by the concentration of the Fe2 plus, all right? So unfortunately, I don't have that written here, so let me just put that here. Q would be equal to the concentration of the cadmium ion, Cd2 plus, divided by the concentration of the Fe2 plus, all right? These would not be involved in calculating Q because those are both solids, right? If you remember when we were talking about equilibrium, remember we said that when it comes to solids and liquids, we do not include them in any calculation of either Q or K. So that's what is being calculated here. Q is equal to the concentration of the cadmium, which is 0.010, divided by the concentration of the iron 2 plus, which is 0.60. And that works out to be equal to 0.0. Well, we didn't calculate that here. We put that here where Q is. And then you do the number crunching for all of this. And the answer is that the standard EMF is equal to 0.013. And because that is positive, because that standard EMF is positive, that means that this reaction is going to be spontaneous, right? And that's basically how we answer that question. Okay, any questions about this? Any questions about this particular example? Any questions? Okay, before we move on to the actual assignment question, so I just want to run through this. These are just examples of batteries. Batteries are basically what we call cells, technically speaking, right? And these are just different examples, and they all have the same underlying principles, right? You have an anode reaction, you have a cathode reaction, and basically, when you add them up, you're going to get the net reaction, all right? In this case here, it's a bit more complex than the ones that we have seen before, but it's basically the same underlying process. So this is an example of a dry cell, you know, the type of batteries that you would use to power your remote controls or whatever other devices that you may have. Here's another one. This one, of course, you'll see these in watches and so on. Again, you have the cathode and you have the anode, and these are the reactions here. That's the cathode reaction, that's the anode reaction, I'm sorry. And this one is the cathode reaction. And again, when you add them up, you're going to get the net equation. All right. Here's another one. Now, of course, this one you'll recognize in your motor vehicles, the car batteries. In this particular case, you have a series of cells, but they act collectively as one. And again, the same principles apply. All right. You have the cathode reaction, which is the reduction reaction. You have the anode reaction, which is the oxidation reaction. And you have the net equation when you add those two together. All right. And then we have this one, which is a bit different because it's a solid state electrolyte that is being used. But again, it's the same principle being applied here, right? So we call this a solid state cell, right? Where we have the lithium acting as the anode and this titanium 4 sulfide acting as a cathode. And basically you have the formation of lithium ions as a result of oxidation of the lithium metal. So basically this is the anode, and electrons will go through the external circuit to power anything that you hook it up to. And then the electrons will end up reducing the titanium 4 sulfide to form this complex right here, all right? So that's basically what happens in this case. And then we have the hydrogen fuel cell. And my understanding is that, you know, engineers and scientists are still working on this. But basically what is happening in this reaction here, I'll just give you the overall equation. The overall equation is basically the reaction of hydrogen with oxygen to form water. And if and when they become successful in perfecting this, then this can be used as an alternative to fossil fuel, which would be very good because, of course, in terms of the environmental impact, water is the product of that reaction, which does, as far as I know, very little harm to the environment. But as I said before, in the case of the other examples, again, this is basically following the same concept. You have the oxidation taking place at the anode, you have the reduction taking place at the cathode, and basically that's it pretty much, right? The hydrogen and the oxygen are basically fed here, and that's where the reaction takes place. It requires a basic solution, so this could be potassium hydroxide or sodium hydroxide in order for this reaction to take place, all right? Okay, so that's basically just a rundown on some examples of cells. Now, I want to point out this example here of a redox reaction, which has the same underlying principles. Now, we all know that if you leave iron metal exposed to the elements, so to speak, you know, water, moisture, oxygen, and so on, rusting takes place. And this is describing basically how it happens, right? So basically what happens first is that the iron is converted to iron 2+ as a result of oxidation, and then another oxidation process occurs where the iron 2+ is converted to iron 3+, right? So basically one region of the iron would be considered to be the anode because of these oxidation reactions. And then the electrons will transfer to another region, which would basically end up reducing hydrogen ions along with oxygen to form water, right? And basically, as a result of the formation of Fe3+, that Fe3+ will combine with oxygen to form the rust, right? So that's basically what happens in the rusting of iron. It's basically a reaction which is electrochemical in nature. Now, with that in mind, there's another application where we can actually protect objects that are made up of iron from rusting. And we do this by using what is called a sacrificial metal, a metal that is more likely to undergo oxidation compared to iron, right? So what happens is that you take a piece of magnesium, which is a sacrificial metal, and you connect it by electrical wires to your iron, in this case, a storage tank, right? So what happens is that instead of the iron undergoing oxidation, it is the magnesium which undergoes oxidation. So if the iron is not undergoing oxidation, that means no rust will be formed, right? Instead, it is the magnesium that will undergo oxidation to form eventually magnesium oxide, right? So therefore, you have protected your storage tank by basically using the magnesium metal as a sacrifice so that you can save your iron, right? So we call this cathodic protection, all right? Okay, so before we move on to the next topic, I want us now to look at some other questions in the assignments. So let me go here, here, and here. Assignment number 7, where is it? Okay, so I take it that you have done number 1. So if there are no questions about that, these are all balancing redox equation problems in both acidic and basic environments. So let me just scroll down to okay, so this question says, create a galvanic cell given the following. And it says on the left side of the cell, you have a 1 molar solution of oxalic acid with a platinum electrode, which is inert. And then it says on the other side, there's a solid iron electrode sitting in a solution of 1.00 m iron 3 nitrate. Finish drawing the cell and label and balance the half equations and overall cell reaction. Calculate the EMF of the cell standard, delta G reaction standard, and K. Show your work. Indicate where all the charged species flow and their identity. Write the shorthand notation for the cell. And it says use, basically they're saying use the table to determine the relevant data, which would be the EMF values, right? And they give you this. So basically this is what you need to complete in terms of assigning what the different parts are, right? Now, according to the question, the left side will have a solution of 1 molar oxalic acid. So what I'm gonna do, let me make this smaller here. So what I'm gonna do is write down here 1.00 m oxalic acid, right? Because that's the left side, right? And then the question says that it has a platinum electrode. So this is your platinum electrode. And on the other side, it says you have a solid iron electron, right? Dipped in the 1.00 m iron 3 nitrate. So 1.00 m FeNO3, 3, all right? And then it says, finish drawing the cell and label the anode, cathode, electrodes. So, okay, so what you'd have to do, in order for you to figure out which is which, you have to look up the half reactions in the table. Now, I've done that already in the interest of time. So let me scroll down here, and I'm going to write down those equations. Okay, let me get rid of these. Oh, you know what? Let me see if I can make this smaller. And let me do this. Nah. All right. You know what? Let me erase. Let me erase these here. Let me okay. Okay, so I looked up the half reactions for these. And in the case of the oxalic acid, the half reaction will be H2C2O4 to form 2CO2 plus 2H plus 2 electrons. And the EMF of that reaction is 0.43 volts. That's the standard EMF of that reaction. And then for the reduction half reaction, it's simply Fe3 plus 3 electrons to form Fe. And the half reaction for that, or the EMF of that, when I looked it up, is minus 0.04 volts, right? So when we add these two, remember now, the number of electrons lost and gained must be the same. So we have to multiply this by 3 and multiply this by 2, and then we add them together, and the resulting cell reaction is going to be 3H2C2O4 plus 2Fe2 plus, 3 plus, to give 6CO2 plus 6H plus, excuse me. Okay, why is this not giving itself? Plus, okay. Plus 2Fe. And when you add these two together, you're going to get 0.39 volts, all right? So at least we have done that part, and that's kind of important for us to answer the rest of the question, because in order for us to identify the cathode and anode, we need to know what the half reactions are, and we need to know what the EMF values are. So I think that's as far as completing the bottom part of that page. So I want you to write this down because I need to scroll back up. So let me know when you're through. Okay then, so let me clear this and scroll back up. So in order for us to label the different parts here, the left side is where the oxidation takes place. So that means that the left side is called, will be the anode. So I'm going to put anode here. I'm going to put anode here. And then the right side will be the cathode. And it says you need to show the direction, let me see here. anode, cathode, electrodes. Well, electrodes are both anode, cathode, all parts of the cell. Okay, we did that already. Oh, indicate where all the charged particles flow. So basically, because anode is where the oxidation takes place, that means that the electrons will be flowing in that direction. All right? As far as the other charged particles are concerned, as far as I can see, the Fe3 plus will be attracted to the cathode, to the iron. I think that's it as far as charged particles, because from the oxalic acid is not charged. So even though the reaction will take place at the platinum. So I think this is it. I think this is the complete answer to this question. Yes, ma'am. What about what?
In the middle. Is that
Oh, thank you. Salt bridge. You mean this right here, right? Yeah, that's the salt bridge. And the salt bridge, if you remember the example that we saw earlier, would contain potassium and chloride ions, right? And I'm not sure if the question asked for this, but I'll just include it anyway. So because there's going to be a buildup of charge here, what will happen is that the chloride will enter this solution while the H plus will enter the salt bridge. And then over here, because there'll be a reduction in the Fe3 plus concentration, that means that the nitrate will go here and the potassium will enter the solution. So I'm not sure the question asked for those, but for future reference, if you're asked, that's how you determine that. All right. Okay. Any questions about this? Any questions? Any questions out there in Zoom? Okay. Now, there's another part of this question, which is on the next page. Let me clear this. Is it okay for me to clear this? All right. So let me scroll down. So the next part is asking for the standard notation for the cell. So basically, if you think back to what we said before, the left side is where the oxidation takes place. So the way you write this down is you start off with PT, the metal, which is inert, so that won't take part in the reaction, solid. And then we draw a line like that, and then the oxalic acid, H2C2O4, right? Aqueous. And then resulting from that would be H plus aqueous, and then CO2, and that represents basically what happens as far as the left side is concerned. Then you draw two lines, and then we're going to do the same thing for the cathode part of the reaction of the cell, which would be involving the reduction of Fe3 plus to Fe, and this would be aqueous. Again, let me emphasize that the state symbols are very important. So let me put aqueous, oh, this should be a gas. And that's it. And that would be the notation, all right? To find delta G standard, remember that would be equal to minus NFE standard, right? What is N? N is the number of electrons transferred. And based on the equation we had before, the number of electrons transferred would be, if I'm not mistaken, 6, right? Yes, because we multiply 1 by 2 and the other one by 3. So it would be 6 electrons transferred. So that would be minus 6 times 96500 coulombs per mole. And by the way, this will be 6 moles right here, right? Multiplied by the standard EMF. Now we calculated the standard EMF already. That was equal to 0.397. So multiplied by 0.39, what did I say? 39 volts. Volts, I'm sorry. And when we work that out, which I've done already, that will be equal to minus 2.3 times 10 to the 5. And the answer here would be joules, all right? In fact, let me take this back. Let me erase this right here. And let me put joules per mole here, right? And you might be wondering where the joule unit comes from. The joule unit would be the same as coulombs times volts. I should have mentioned that earlier, right? If you have done any physics, especially when it comes to magnetism and electricity, then you would have met these units, the relationship between the joule unit, the coulomb unit, and the volt unit, right? So please remember this, joule is the same thing as coulombs times volt, right? Okay, so this is delta G, which is what the question is asking for. The question is also asking for K. And remember now, the relationship between delta G and K is that delta G standard is equal to minus RT, L, and K, which means that K would be equal to minus e to the minus delta G over RT. So we have to put in the values here. Minus delta G, which is minus 2.3 times 10 to the 5 joules per mole, right? Divided by R, which is 8.31 joules, times the temperature, which is, if I'm not mistaken, 298 Kelvin. And when I did this calculation, I got 4 times 10 to the 39. All right, and that's the answer that I got. All right. Okay, any questions about this one? Any questions? Any questions? No questions? Is it okay for me to clear this? Okay, let me do that now. And let's move on to the next page. Okay, so in this question, they're asking for you to calculate the standard EMF value, the delta G value, standard, and the K value, and it gives you this equation, all right? So let me see what you can do with this. Let me hear your ideas. What would be the very first step in solving this particular problem? What would be the very first step you would do? What time is it? Oh, shoot, I didn't realize it was that late. All right, tell you what, we'll stop here because this will take some time for us to solve. All right, but in the meantime, you can look at it at home, and when we come next time, we can discuss it together, all right? Okay, so that's pretty much it, folks. See you on Wednesday. Oh, by the way, let me see if there's anybody who came in late. Before I forget. Let me see here. Powers is here. Renfro, I don't see Renfro. Salvador, I don't see Salvador. Okay, I think that's it. Yes, ma'am.
I just realized that the assignment number 5 was due the other day, but not today, because I got it confused with today's due date for assignment number 6. Is it okay if I send it to you through message?
You can email it to me.
Yeah, and then another question was,
What was assignment 5 again? Assignment 5 was
it was, I just realized it's on Friday. I thought it was today.
yeah, I'm trying to remember what topic assignment 5 covered. Anyway.
And then you had 2 additional questions, but I wasn't sure which ones it was. Because you have, for assignment number 5, you have this one.
Oh, yeah, so you're gonna attach
This,
that assignment 5.
but then you also had another one, that we did together. Yes, we did this one together.
Oh, no, that won't be part of the assignment. That was just an extra,
Okay,
example that I thought you guys should
okay,
learn, but that won't be graded. Just the two assignment 5, the assignment 5 and the assignment 5 addendum.
okay. Have a good one.
You too. All right, you guys out there in Zoom, Lisa.